So every Riemann integrable function implies that the function is Lebesgue integrable. So we are now going to prove that every Riemann integrable function defined on a bounded interval is Lebesgue integrable. The function is bounded, defined on the closed interval AB, and assume that f is bounded and a Riemann integrable. So that the lower bound is small m, upper bound is capital M. Now let us talk about the partition. By partition, we mean set a point of the interval. The first point of the partition is the left hand point of the interval, and the last point is the right hand point of the interval B. So then we define the basic interval I1. The basic interval I1 is the interval starting from x0 and ending at x1, closed at the left, often on the right. So then we define capital Ij's, xj minus 1, xj, that is closed on the left, often on the right. The last interval in is defined xn minus 1, and b, this is a closed interval. Then refinement of partition. So a partition P2 is said to be refinement of another partition P1 if P2 is superset of P1, and P3 is a refinement of P2, P3 is a superset of P2, like that. So then the mesh or norm of the partition PK is defined as the maximum length of the interval delta j, where delta j is the length of the interval or measure of the interval. Okay, so the partition has so many points. Joining two two consecutive points makes you a basic interval. Then you can talk about the length of the basic interval, and then the maximum of all these basic interval, that we call it norm of the partition, denoted by pk norm. And if you get on refining the partition, then the length of the interval gets reduced, and as k tends to infinity, then the norm of the partition tends to 0. That is what we have here. So that is the refinement of a partition. So then let us talk about the extremal values, that is the infimum and the supremum in the subinterval. Small mj is the infimum of the function f of x in the subinterval ij, and capital mj is the supremum of the function f of x in the capital interval ij. So in each interval we define the infimum and supremum. They are called the extremal values. Okay, so and then we talk about the lower double sum. So it is denoted by LFPK, and it is exactly equal to the sum of the product of the length of the basic interval into small mj, and it is obviously greater than b minus a times m, the lower bound of the function in the whole interval. So this is lower double sum. Then we talk about upper double sum. It is denoted by UFVK for the partition PK, lower upper double sum, and it is also defined as sum of the product of the length of the interval and a capital MJ. So it is obviously less than b minus a times am. So this is upper double sum of a partition PK. And then we talk about delta j, the length of the interval or measure of the interval, basic interval ij. Okay, so this is how we define for a partition upper double sum and lower double sum. Let us visualize the upper double sum and a lower double sum for a particular partition. Let us see upper and lower double sum for Riemann integrability. Okay, so for simplicity, we have a partition PK. It consists of only 2 points, A and B, and it has only one basic interval, the original interval. So f of x is the graph of the function, that is green graph, and C the area bounded by ordinate at A, ordinate at B, graph of the function, line segment A to B. This area represents the Riemann integral of the function. So, and then we talk about, in this interval, we have only one interval, basic interval, the originate interval. And the infimum mj is the height or the ordinate at A, and the supremum is the height or ordinate at B, capital Mj. This is the parameter we have. So with this one, now let us see the upper double sum and a lower double sum. So there is only one basic interval ij, that is the original interval. Length of the interval is b minus a, mj infimum, capital Mj the supremum. So these are the parameters we have graphically here. Here, as I mentioned earlier, this area, green shaded region, is the Riemann integral, and the Riemann integral is denoted by r, putting r. So this is the Riemann integral. Then let us come to the upper double sum. This is yellow dotted line and the horizontal line. This rectangle, that is what? This rectangle is this much height and this much length. Okay, so area of the rectangle represent the upper double sum. For this particular partition, this is mj times b minus a. Then let us see the lower double sum. This is the yellow shaded region. This is the upper double sum. This is UFPK, and then obviously UFPK is greater than the Riemann integral. Then let us see the lower double sum, the red dotted line, and it is denoted by LFPK MJ B minus A. That is precisely the area of this region, the red shaded region. This is the lower double sum for the particular partition PK. Okay, so it is precisely less than the Riemann integral. So we have this basic inequality, LFPK less than Riemann integral less than UFPK, the upper double sum. So this is the visualization for a particular partition. The upper double sum is always greater than a Riemann integral, and then it is greater than the Lebesgue integral. Okay, so double sums of refined partition. Let us see. After refining the partition, the upper double sum gets reduced, the lower double sum gets increased. So the original partition PK has only two partition point A and B. This is the original partition PK. This is the graph of the function, and we have this basic inequality LF PK less than or equal to R integration a to b fx dx, that is the Riemann integral, less than or equal to uf pk. This is the relationship. Now let us introduce a new point C, and we have new partition pk plus 1. So it has one more point than the earlier partition. Therefore pk plus 1 is a superset of pk, and therefore it is a refinement of pk. Okay, then it has two interval, basic interval, I1 on the left of C, I2 on the right of C. Length of the interval I1 is obviously C minus A. Length of the interval I2 is B minus C. So in the interval small I in the interval I1, small m1 is the infimum. The extremal values infimum is small m1, and capital M1 is going to be the supremum, and this much height is the supremum. So that is obvious. And then in the I2, the infimum is small m2, and in I2, the supremum is capital M2. This is obvious. This is obvious. Now let us find out the upper double sum. The upper double sum is the sum of the two rectangles bounded by the yellow dotted line. So that is precisely the upper double sum. The yellow shaded region is the upper double sum for the defined partition pk plus 1, and it is precisely the area of the smaller rectangle, that is capital M1 times C minus A plus M2 times B minus C, the area of the bigger rectangle. So this represents the upper double sum of the refined partition pk plus 1. Let us compare with the upper double sum of the partition pk. So obviously UFPK is greater than UFPK plus 1. So if you refine the partition, the upper Darboux sum gets reduced. This is obviously from the picture you have seen this one. The upper Darboux sum decreases. So in the inequality also UFPK, the upper Darboux sum less than, the refined partition upper Darboux sum is less than. Now let us see the lower Darboux sum. So the lower Darboux sum is the red shaded region. This is precisely, some of the area of the two rectangles, that is LFPK plus 1, the lower Darboux sum for the refined partition M1 C minus A plus small m2 B minus C, that is the sum of the two areas. That is the lower Darboux sum for the partition PK plus 1. And let us compare it with the lower Darboux sum for the partition PK before refinement. So it is obviously clear that LFPK plus 1 is greater than LFPK. So if you refine the partition, lower Darboux sum increases, whereas upper Darboux sum decreases. So you have this basic inequality. This is true for each refinement partition. This is true for each partition you get on refined. Okay, now let us see visualization of simple function. Then let us talk about the simple function. Because Lebesgue theory of integration, we define integration from the simple function. So what is the simple function from this construction? So for the partition PK, it has lots of partition point, and in this interval Ij, we define UK. If x belongs to the Ij, the UK function is capital MJ. If x belongs to Ij, the LK function is small mj. So like that, you start defining the function in its basic interval. See, in a given interval, the red shaded strip represent LK in a given interval LK. So it is precisely below the graph of the function, green graph. Therefore, LKX for each k is less than the function value f of x. Okay, and in this interval, again, the UKX, the yellow shaded strip, is above the red shaded one. Therefore UKX is greater than, it is supremum function greater than the LKX in the same interval and the horizontal line segment. But the yellow function or the yellow strip, it is above the graph of the function. Therefore it is also greater than f of x. This is precisely represented graphically here. UKX is greater than f of x, and f of x is less than LKX is less than f of x. So then let us see, if you refine the partition, what happened? If you refine the partition, the gap between the yellow strip and the red strip gets reduced. That means the gap reduced, the gap is reducing. Okay, see, if you refine, so L1x less than L2x, and then it is less than f of x, then less than U2x, U1x, like this. So if you refine the partition, the two functions closer and closer to the original function f of x. That is what we have seen. Then we define the UKX in totality, LKX in totality, like this. Sum of the linear combination, sum of the j running from 1 to n mj and a chi ij. This is, we call it simple function. LKX is equal to sum j running from 1 to n mj chi ij. So these are two simple function. So you know that the simple function, these simple functions are measurable because the interval ij's are measurable. Therefore UKX is a measurable function, LKX is a measurable function. So these measurable functions are all Lebesgue integrable. Now we have constructed Lebesgue integrable function UKX and LKX. Okay, and we have this basic inequality. This is we have seen. So LKX and UKX for each k, you have a sequence of function, LKX, UKX, you have sequence function. Each function is measurable and they are Lebesgue integrable and they are bounded by, the function, the capital M and the small m. So this sequence of function are bounded function. So they pointwise converge to another function Lx and Ux. And the pointwise limit Lx will be less than f of x. And pointwise limit Ux will be greater than f of x. So this is what is happening. Okay. So then let us see the pointwise convergence of simple function. Let us see. Yeah, pointwise convergence of simple function graphical visualization. Let's say this is the graph of the function, and this is LKX and the UKX, U1X, L1X is there. Then if you get a defined partition, then U2X closer to f of x, L2X closer to f of x. Okay, this is the thing. Yeah, this is, so it goes, the gap is closing and ultimately converging to the function f of x. So as k tends to infinity, LKX converges to, pointwise converges to Lx and UKX converges to Ux. So this is what you have seen. Okay, yeah. And then, since LKX is measurable and Lebesgue integrable, Lx is also measurable and Lebesgue integrable. And similarly, Ux is also measurable and Lebesgue integrable. So that is, we have, we have seen this one, we have done this one in the theory classes. If you have a sequence of function, their limit function is also measurable if each function is measurable. So that is the thing. Yeah, we have Lx, Ux, and then this inequality is very important. Lx is always less than f of x, and it is always less than Ux. Then the simple functions are measurable. Their pointwise limit function is also measurable. So this is what we have. Pointwise limit preserve measurability. So Lx, Ux are Lebesgue measurable function. So we have defined Lebesgue measurable function, Lx, Ux. Then let us talk about Lebesgue integral of simple function, this simple function, and their limits function. So Darboux sum, Lebesgue integral and Darboux sum. Let us see, visualize again. F of x is here, graph the function. Then LKX is there, and then Ux is there. So this is precisely, LFPK. The lower Darboux sum is precisely the Lebesgue integral of the simple function Lk. The Lebesgue integral of simple function Lk is exactly equal to the lower Darboux sum LFPK for the particular partition Pk. This is very obvious from the diagram. Again, the upper Darboux sum is precisely the Lebesgue integral of the UK function. Okay, so UK function. Then if you get on refining the partition, so then k tends to infinity, the norm of the pk tends to 0. Then since f is Riemann integrable, since f is Riemann integrable, that is exactly equal to the Riemann integrable. So what is this? What this must is exactly equal to lower Darboux sum, and if k tends to infinity, since the partition norm tends to 0, this is exactly equal to Riemann integrable. And similarly here also the upper Riemann integrable. Okay, this integral is exactly similar to the upper Darboux sum, and as k tends to infinity, the norm of the partition tends to 0. Therefore this limit is exactly equal to the upper Riemann integral, and since it is Riemann integrable, the upper Riemann integral is exactly equal to lower Riemann integral, and that equal values we call it Riemann integral r a to b. That is exactly happening here. Okay, so this is the thing what we have from the construction is that next application of dominated converse theorem to sequence of simple function. Now let us apply dominated convergence theorem. You see, dominated convergence theorem, the sequence of functions are dominated or less than a given function. You see, if you take gx maximum of small m norm and capital M norm, that function gx will be greater than is function lk and is function uk. Okay, so that is, and this constant function gx is measurable and it is Lebesgue integrable, you know. So what we have is that, what we have is that, so this gx is a constant function and this is greater than is ukx and this is also greater than is lkx. So is ukx, is lkx is Lebesgue measurable function dominated by gx, which is Lebesgue measurable as well as Lebesgue integrable. So is function is Lebesgue integrable. So by Lebesgue's dominated convergence theorem, what we have is that, this this equation, what we have is that, so if this limit go inside this integration, what you get is L. If limit go inside the integral, then you are going to take limit k tends to infinity to lk. When limit k tends to infinity, lk is L. So that is exactly what here. So this is given by the Lebesgue dominated convergence theorem. This is integration L d mu. L d mu represent the Lebesgue integration. Okay, so here you have this equality. This is coming directly from the Lebesgue dominated convergence theorem. Okay, so here also you see, yeah, let us talk about this integration. Okay, by Lebesgue dominated convergence theorem, is ukx is less than gx and gx is measurable and integrable, therefore uk also measurable and integrable, and this limit can go inside the integration. So if this limit go inside the limit of the integration, then you are going to take limit to uk. So if limit is taken on uk, you get u. So that is why this equality is here. But this is exactly as k tends to infinity. What is this? This is a Riemann integral. Okay, so from this equality, what do you get? Integration u d mu is exactly equal to integration L d mu. So this is what you have. This is what you have here. So then if you change the side, you get this equation. Integration u minus L d mu is equal to 0. Then what do you get? So in Lebesgue integration theory, if a function's integral is equal to 0, then the function is almost everywhere 0. That is what we have from the theory, Lebesgue theory of integration. So yeah, function is equal to a Lebesgue integrable function almost everywhere. So let us see graphically what does it mean. Let us visualize it. Equality almost everywhere. Let us see. Almost everywhere means the function equal to another function except a set of measure 0. So you have, L, you have u function, you have L function, and what we have is u is equal to L almost everywhere. There are some points where they are failed to equal. That is, ux is obviously greater than, strictly greater than Lx. So the set of points where they are not equal, its measure equal to 0. Yeah, you see in this blue dotted points, the two functions are clearly, visibly different. One is above the line, another one is below the line, different. The set of this collection of points is denoted by E. Its measure is equal to 0. That means ux is equal to Lx almost everywhere, and ux is greater than f of x, and f of x is greater than L of x, and Lx is equal to ux almost everywhere means all these three functions equal to almost everywhere. Okay, then what is the conclusion we can draw here? This Lx, these are measurable and Lebesgue integrable. This ux, these are measurable and Lebesgue integrable. And these three functions are equal to, almost everywhere. Therefore, this function f of x is also measurable and Lebesgue integrable. So that is the thing. And integral of this function is exactly equal to integral of this function and integral of this function. But what is the integral of Lx? The integral of Lx is Riemann integral. Okay, that is why the conclusion comes here. This is integrable. Its integral is exactly equal to integral of this one. But what is the integral of Lx, Ux? Its integral is a Riemann integral. Okay, that is the thing. That is the final conclusion. You can draw it. Yeah, this is the conclusion. Okay. So f is Riemann Lebesgue integrable. Its integral is equal to integral of L. Why? Because f is equal to L almost everywhere. But the integral of L is nothing but Riemann integral. So every Riemann integrable function is Lebesgue integrable. The conclusion is here. This is a very fundamental theorem. Now let us see. The converse is not true. There are Lebesgue integrable functions which are not Riemann integrable. Counter example, let us see. This is famous example, okay? The function f of x defined in the closed interval 0 and 1. And if the point, if the point is a rational number in 0, 1, the value of the function is 1. This dotted line represent the value of the function at the rational point in the interval 0, 1, and 0 if the point is an irrational number in the interval. So yeah, this is a very famous function, and this function is defined a closed and a bounded interval, and it is a bounded function. Okay, it is bounded function, and it is Lebesgue integrable, but it is not Riemann integrable. Let us see the Riemann integrability. Riemann integrability. Let us see what is lower Darboux sum of partition of any partition P is lower Darboux sum is 0, because in each partition what you have, in each partition there are rational number as well as irrational number. So infimum will be 0 and supremum will be 1. So therefore LFVK not equal to UFV. Okay, never where they are not equal. So it is not integrable, not Riemann integrable. Okay, this function is not Riemann integrable. Let us check the Lebesgue integrability. The set A, that is a rational number. The B is the set of irrational number. The measure of A is obviously 0. The set of rational number is countable. Measure of B is precisely 1, the length of the interval. So then the function can be break up into two parts, characteristic at A and characteristic at B. So at B, the value of the function is 0. At A, the value of function 1. So the function now has been translated into a simple function. This type of function is a simple function. Therefore, by the definition of Lebesgue integral of simple function, its value is equal to 0. It is Lebesgue integrable, but not Riemann integrable. So this is an example, excellent example, which shows Lebesgue integrability. Okay, let us stop here.